The other new test for today is the root test. It actually has the same framework as the ratio test. It's just that the limit that we look at is a little bit different. And so again, we're going to look at the series a sub n, and this time we're going to let rho be equal to the limit of the nth root of the absolute value of a sub n. So in other words, we're just taking the individual terms, we're taking the nth root of them, and then we're taking the limit. And so the conclusion of the root test is exactly the same, where if rho is less than 1, the series converges absolutely. If rho is greater than 1, the series diverges. And if rho is equal to 1 or the limit doesn't exist for some reason, then you have to do something else. And so the intuition for this is actually very similar to the intuition for the ratio test, which is that if we know that rho is approximately equal to the nth root of the absolute value of a sub n, that's the same as saying, roughly, that the a sub n term is approximately equal to rho to the n. And so this is exactly of the form of a geometric series again, because we're just saying that a sub n is just rho raised to the n, and so a n plus 1 is rho to the n plus 1, and every time that you increase n by 1, you're just multiplying by rho. So this is just another way of comparing any series to a geometric series. The usage for the root test, though, is a little bit different than the usage for the ratio test. And so the root test is good whenever you have an n in a base and a power. And so what I mean by that is things like n to the n, or maybe even functions of n. So maybe something like ln of n to the n, or maybe if the function is in the power, anytime when there's an n both in a base and a power, then the root test is at least something to consider. And then the root test is going to be bad, just like the ratio test for ratios of polynomials. And so again, that's things like k over, maybe this time, k to the third minus 9. And so here, the limit comparison test would work really well for this, but the ratio test and the root test are both going to be inconclusive. So now let's look at a couple examples. For this one, we have the sum of 1 over n to the n. Already, you would be able to show that this converges using direct comparison, because n to the n explodes really quickly. It's bigger than n squared, and so overall we could say that the series is less than 1 over n squared and be done with it. But I want to look again at how the root test would handle this. And so we take the limit as n goes to infinity of the nth root of the absolute value of n to the n. First of all, that absolute value does nothing, because these were already positive to begin with. And then if I just take the nth root of this, I should have written this in the denominator. Let me fix that. Sorry. This should have been 1 over n to the n. And so if I take the nth root of this, then I'm going to get the limit as n goes to infinity of 1 over n, just because the nth root and the power n here just end up canceling. And so this limit ends up being equal to 0. And so from the root test, this converges. All right, the next one is a little bit more challenging, and as you'll see, some of the problems with the root test end up requiring you to use L'Hopital's rule. And so here, this is a good candidate for the root test, this series, because again, there is an n in the base and an n in the power. And this time, they're both really functions of n, but still, the fact that there's an n in a base and an n in a power anywhere means that the root test is at least something to consider. And so here, we'll take that limit as n goes to infinity of the nth root of 1 minus 1 over n to the n squared. So now we have to remember how power rules work, and the nth root is really the same as taking the 1 over nth power, and then powers end up multiplying together. And so in other words, I could rewrite this as the limit as n goes to infinity of 1 minus 1 over n to the n squared times 1 over n. And so the n squared is going to partially cancel with the 1 over n. And so I'd get the limit as n goes to infinity of 1 minus 1 over n to the n. All right, this here, though, is annoying, because it's really tempting at this point to say that the base right here tends to 1, and so 1 raised to any power is 1, and then we're done. That's not true, though, because, and it maybe has been a little while, but 1 to the infinity is an indeterminate form for L'Hopital's rule. And the reason is that if this power goes to infinity really quickly, then because these terms are all less than 1, maybe they'll end up going to 0 overall when you take a really large power, or maybe it's something between 0 and 1, or maybe it actually is 1, and we can't tell unless we do a further analysis. And so in order to deal with the fact that the n's are on different levels, one in the base and one in the power, there's this common trick which you'll have to use in some of the problems we see coming up, which is to rewrite the base as e times ln of the base. And so in other words, I'm just rewriting so that everything can be on the same line. And so this will be the limit as n goes to infinity of e to the natural log of 1 minus 1 over n. And then I still have that times n out front just from the power originally before. And so at this point, I have to figure out what the limit is of this part right here. And that's essentially a separate mini problem, which I can do right now. And I'll actually bring it up over here where there's a little bit more space. And so now I need the limit as n goes to infinity of n times the natural log of 1 minus 1 over n. And so if I were to look at this limit and see what happens to each of the terms, the first one goes to infinity, the second one goes to natural log of 1, which is 0. So again, this is infinity times 0, which is indeterminate, and so I need to rewrite it in order to figure out what the limit is. And the trick for that is to rewrite it all as one fraction. And so in other words, I'm going to convert the n to 1 over n. And now the numerator and the denominator both go to 0 as n goes to infinity, and so I am justified in using L'Hopital's rule, which I meant to put above the equal sign. I'll just move that. And then I can take the derivative of the top and the bottom. So the derivative of the top is 1 over 1 minus 1 over n, and then I need to multiply by the derivative of what's inside because of the chain rule. And so the derivative of what's inside here is the derivative of a minus 1 over n, which ends up giving me a positive 1 over n squared. In the denominator, the derivative of 1 over n is minus 1 over n squared. And now, fortunately, even though that maybe seemed like quite a bit of work, we can take the limit at this point because these n squareds end up canceling. This 1 over n just goes to 0, and so we have a whole bunch of 1's everywhere and 1 minus 1 in the denominator, and so overall this limit ends up being minus 1. Right, so this was all sort of an aside, and now I have to trace back and see what that corresponded to in this problem. It's just telling me that the part in red that I had circled here, I can just replace with a minus 1 when I take the limit. And so this limit ends up being e to the minus 1, which you've probably seen before, but if you haven't, that's a bit of a surprising fact that this limit would end up being anything involving e, but it does. And so 1 over e, or e to the minus 1, is less than 1. And so if we jump back to what the root test was saying, because this is less than 1, the series converges. And so this would have been a really hard one to have any intuition for. By just looking at this series, it's hard to know whether it's going to converge or diverge, but we could conclude using the root test that it does converge.